Okay, so I don't think anybody else probably is not going to join in. So I think we will get started with this training. Um, you guys can unmute your mic if you can. So before we start the training, I would like to do a round of introductions. You guys first, then I'll introduce myself. And I would also like you to tell me whether you are a student, are you working somewhere, and what is your expectation from this training program. So later on, I'll introduce myself and then I'll explain the contents of the training program, what are the main highlights, and how we are going to progress one by one. So please, yeah.
Hello, I'm Fahad Taked. I'm a recent graduate from the University of Texas at Arlington.
Okay.
I I hope currently I'm living in Texas. I hope to get a job after this training.
So you have finished your master's program there, your grad program?
Yeah.
Okay. So fine. And what was your major? What did you major in?
Electrical,
Electrical.
and my major was embedded systems.
Electrical. What was the second one?
Embedded,
Embedded systems. Okay. Okay.
yeah.
Fine. How about you, Nathan?
Hi, so I graduated in May 2020 with Masters in Electrical Engineering with a specialization in digital design and verification.
Okay.
And as of now, I'm working as an intern at CTI1 Corporation as an embedded software engineer.
Okay.
So,
And you're trying to get back into VLSI, or is that your aim to find a job in as a VLSI engineer somewhere? That's why you're learning this?
yeah, that was always this was just a backup plan to work in an embedded field.
Okay. Okay. And where are you both guys based?
Now I'm in San Jose, California.
You're in San
I'm
Jose,
in
and
Texas.
in Texas. Okay. Yeah. Sorry, you mentioned that. Yeah. Okay. So this timing is okay for you guys?
For me, it's not actually. It's 5 a.m. here, so
Yeah. Nitin will be little. Um. Okay. So I'm just asking. So do you want to push it back by 1 hour or something, or that doesn't work for you, Fahad?
It works fine.
Okay, let's discuss it. And to at the end of this class, the training schedule, the timing part. Okay, so let me introduce myself. My name is Yogesh Torvi. I have a master's degree in VLSI and embedded systems. I have been working in the ASIC and FPGA design field for the last 20 plus years. I was in US for a few years. I have lived all along the West Coast, Seattle, Portland, San Jose. I was in Canada for a few years. I came back to India. I'm in Pune right now, based in Pune. Here I'm running my own consulting and training company. So design, consulting and training also. So that is where I come in as a trainer here for Verilog in this case. Uh, so I worked on FPGA design using Verilog and VHDL. I worked on ASIC design. I worked on embedded systems, algorithm developments, etc. So that's pretty much. I mean, overall system design, depending on what is required. This particular training program is for Verilog. So the focus will be on Verilog. Initially, I would quickly refresh digital logic design concepts. I won't teach them in details. Just quickly refresh them. Followed by number systems, also part of digital logic design. Quickly refresh that. Then we'll go and look at FPGA architecture briefly. Though it is not part of Verilog design, I would like you to understand that just very briefly what FPGAs are and where Verilog fits into all of this. So if you design something in Verilog tomorrow, how would you make, because ultimately Verilog is a hardware design language, HDL. So you're using Verilog because ultimately you would want a working chip somewhere. So how does Verilog fit into the scheme of things? So that's what I want you to understand. So we'll look at FPGA design methodology. and briefly what FPGA is, and then we will start Verilog in detail. And then we look at Verilog step by step in detail. What is the history of Verilog? Then the syntax for Verilog. How do you design digital logic circuits using Verilog? It could be combination, basic gates, combinational circuits, sequential circuits, memories, FSMs, etc. So that is the Verilog part. Then once you do Verilog design, you would like to test your design. So how do you write something called a test bench in Verilog again? And you test your design. So how do you do that? That's the next part. Once you write the design and the test bench, you would like to simulate it. We call that functional verification or simulation. So how do you do your simulation? How do you generate timing diagrams? How do you analyze the timing diagrams to make sure that the design and the testing is correct? And once that is done, so we will do that for a lot of examples actually. And towards the end, I would ask you to practice some examples on your own. I will give you some tasks and examples to practice out on your own. At which point, I will ask you to install the Xilinx software on your laptop or desktop. If you already have it, that's fine. If not, you can download it and install it, and it's free of cost. And you will use that for your simulation purpose. So, towards the end of the training program, that is the activity that I will be asking you to do it, to write the design, to write a test bench, to perform simulation, and explain what you have done. And just briefly, during the Verilog training, we will mention about, since we are talking about FPGA at an introductory level, I will explain to you very briefly what are the back-end steps required to convert your Verilog design to a FPGA system. Just as a brief explanation, so you understand what goes behind after the design is done. That's more or less. So the focus is on Verilog, but the other parts will be briefly introduced and taken just for your understanding, better understanding of the whole process. Does this sound okay to you? Does this sound something that you will be okay with?
Yeah, this
Yeah.
is fine.
Okay. And typically my sessions go on from anywhere between 1 hour to 75 minutes, 90 minutes. I don't take beyond that because the focus goes away. The schedule will be every alternate day. Only this week, they asked me to start the program. So today is Thursday, and tomorrow we'll have another class on Friday. But next week onwards, it will be Monday, Wednesday, and Friday evening my time. So it will be every alternate day. The actual timing part, let's discuss it towards the end of the program. If the starting time can be pushed back by an hour or so. So especially for Nitin because he's pretty early for him there. So let's look at that at the end of the program. So just give me a minute. I'll share my presentation with you and then we'll start. Okay, so can you see this digital logic design? Yeah, just a second. Can you see this digital logic design slide?
Yeah.
Okay, so we'll quickly go through the basics of digital logic design. You might remember some of it or most of it, but I would like to just quickly go through it anyways, because this is very important from Verilog perspective. So digital logic design, as you know, consists of basic gates, combinational circuits, sequential circuit. These are the three main types of circuits involved. Basic gates are your basic gates, and or NOT gates, NAND gate, NOR gate, etc. Uh, Transistors are the fundamental base of any chip. CMOS transistors. Gates are made up of transistors. And as you know, you might have come across Moore's law when you studied your various subjects. So Moore's law says that the number of transistors will double on the chip every 18 months to 2 years. So that has been true for the last 30 odd years now. So as more number of transistors are available on the chip, more number of gates and more logic can be implemented on the device or the chip. So as we go area, we can implement more and more logic gates and more logic on the same device, since more number of transistors are packed into the same device. Let's come back to the basic gates. These are some of the basic gates: AND gate, OR gate, and NOT gate. If you see here, on the left hand side is the symbol of the gate, and on the right hand side is the truth table for it. So AND gate is if both inputs, if it's a two input AND gate, both inputs are 1, output is 1, otherwise output is 0. OR gate, any one input is 1, output is 1, otherwise it's 0. NOT gate, any input is inverted, 0 becomes 1, 1 becomes 0. NAND gate, this is a truth table. So if one of the inputs is 0, output is 1. Both inputs are 1, output is 0 for a NAND gate. NOR gate is the reverse. If both inputs are 0, output is 1. If one of the input is 1, the output will be 0. That's how NOR gate will work. Then we have XOR gate. XOR gate is if both inputs are different, 0, 1 and 1, 0, output is 1. If both inputs are same, 0, 0 and 1, 1, the output will be 0. That's how a two input or XOR gate or two input XOR gate will work. This is just a tabular format for the same thing. And or inverter. Buffer is just, it will continue. It's used for if you have a high fan out or if you need more driving capability, you have a buffer in place there. Otherwise, buffers are not used. NAND, NOR, XOR, and there is something called XNOR, which is reverse of XOR. So XOR means if both inputs are different, output is 1. In this case, XNOR, if both inputs are different, output is 0. If both inputs are same, then output is 1. In that case, it will be implemented as a XNOR gate. We know that NAND gate and NOR gate, both of them are called universal gates. Means what? Any other gate like AND gate, inverter, or OR gate can be implemented using NAND gates. So this is just a slide to show that just using NAND gates, we can implement the other basic gates like AND, inverter, and OR gate. So NAND is called a universal gate. Same is true for NOR gate. NOR gate is also called a universal gate because same concept. Using a NOR gate, only NOR gates, I can implement other basic gates: OR gate, AND gate, and inverter. So NOR and NAND both are universal gates. These are some standard ASIC devices available, standard chips that are available in the market that you can buy and use directly. If you see here, for example, 7432 device has 4 OR gates. Each OR gate is a 2 input OR gate. And some other devices that you will see here, this have been around for a very long time. So these chips are available in the market, and each of them has this basic gates as a part of the chip. The functionality of this chip will not change. So if this is a AND gate 7408, this can act as we can use 4 internal AND gates for our purpose if we want to use them. At any point of time, if you have any question, please raise them. This is how the integration level have progressed over the last 30 odd years. It started out with something called SSI, small scale integration, late 60s, early 70s. Very few gates, 1 to 10 gates. Then it went beyond up to 100 gates, where it was called medium scale integration. Integration means number of gates on a chip. Then it went to LSI, was large scale integration, which went up to few thousand or 10,000 gates. And then after that, it went beyond 10,000 gates, where it was called VLSI. We still call it VLSI. We don't call it V square LSI or V cube LSI. Whereas right now, if you look at the transistors, the chips today in the market, you'll have millions and millions of gates. The biggest chip available right now is having close to 1 billion transistors on a single chip. So that's the kind of integration that we're looking at right now. The node, the technology node as we call it. Today, the latest node that people are manufacturing at is around 7 nanometers. That number Can you tell me what that number denotes? If I say 7 nanometer technology node or 10 nanometer technology node or 20 nanometer technology node, what does that denote?
The size of the
Size of the,
gate.
okay, any other answer or any more explanation to that? What is the most basic part on the chip?
The transistor.
Yeah, it is the transistor. So can you define in terms of transistor?
So the number of inputs and outputs. So a NOT would be a two node.
But we are talking about technology node. So let's say I'm talking about this chip is manufactured using 10 nanometer node. So what does that mean?
I don't know.
Okay, rather than size of the gate is the size of the transistor, right? The cross section of the transistor to be more specific. So one transistor, when let's say if I say this chip is manufactured with 10 nanometer technology node, means one CMOS transistor cross section size is 10 nanometers. So then you can pack, uh, if you see the history of the technology nodes, it has reduced in size. It started somewhere with 180 nanometers, now it is up to 7 nanometers. So that means the size has reduced. What is really reducing is the size of the transistor, single transistor. So if the size of the transistor is reducing, that means in the same area I can pack in more transistors, right?
Yeah.
So that is how I can get more and more and more transistors in the same chip size. Even chip sizes have increased, but if you compare apples to apples, in that case, the same chip size, if earlier it can hold up to, let's say, 1 million transistors, now can hold up to 10 million transistors or maybe more, because the transistor size is reduced. So that's how this integration that we're talking about here. It is still called VLSI. It is not, the nomenclature stopped at VLSI. We don't call it V square or V cube or something like that. LSI. So that's what VLSI means for you. And those transistors make up gates and other logic, and those gates and other logic will be designed using Verilog. So whatever you write in Verilog will ultimately get converted to gates and then ultimately to CMOS transistors, and that logic on CMOS transistors will work on the chip. That is what will ultimately happen. That's why you, instead of doing transistor CMOS level design, which is very very complex, or gate level design, which is also relatively complex and time consuming, you have a language called Verilog or VHDL, where you can design the circuit relatively easily and use some other tools to convert your Verilog code to gates and transistors. And on the chip, it will be gates or ultimately transistors that will work on the chip. Okay, so that's why you are learning Verilog, to make that happen on the chip. Okay, so that was about basic gates. Now we talk about combinational circuits. Combinational circuits are such where output is dependent only on the current input. There is no history, there is no memory of other inputs earlier. Whatever current inputs and the logic of the circuit, combinational circuit, the output will be generated. So output is function of current input. It helps in reducing design complexity and the chip count when we compare this to CMOS logic. So CMOS logic will be very complex. If you, I don't know whether you've done CMOS design like inverters and stuff before. Very simple thing like an inverter will also be very complex to design, based on, if you have, some people like analog design, for them it's very interesting. I don't really like analog design to work on CMOS, so for me it was not really interesting for me. So it is, you have to really understand MOS logic well and design based on that. So if you take combinational circuit, which is part of digital logic circuit, it will help you in reducing the complexity of the design, and the overall logic will also be smaller because many transistors will make one gate, and then such gates can be designed and connected with each other. So we look at some of the useful combinational circuits used in digital logic design. Excuse me. Multiplexer is one such combinational circuit. So how does a multiplexer work? We have a 4 is to 1 multiplexer here. There are 4 inputs, there is one output, and which input goes to output is determined by the select lines. There are so n number of select line, 2 raised to n number of inputs, one output. That is how a 4 input or any multiplexer will work. So since there are 4 inputs, I need 2 select lines. 2 raised to 2 will give me 4. And how does this work? If S1, S0 select line is 0, 0, I0 input, whatever the value will go to output. When it is 0, 1, I1 value will go to output. When it is 1, 0, I2 value will go to output. When it is 1, 1, I3 value will go to output. That is how a 4 input multiplexer works. Similarly, we can have a 8 input multiplexer where you'll have 8 inputs. So to have 8 inputs go to the output, we need 3 select lines because there are 8 inputs. So depending on the select line, one of the inputs between I0 to I7 will get routed to the output. So what if I want to design a 16 is to 1 mux? How many select lines will I need?
4.
Excuse me. If I want to design a 16 is to 1 multiplexer, how many select lines would I need?
4 select lines.
4 select lines. Okay, what if I want to design 20 input multiplexer?
You need to 5.
5 select lines. With 5 select line, how many inputs can you technically service?
32.
32. So what will happen to the other 12 inputs?
They won't be used.
Right. You can leave them floating, or to make sure they are not used, you just ground them and use the other 20
Yeah.
that are required. Right. So that's how you design using multiplexers. So coming back to this, yeah, those multiplexers are also available as standard chips in the market. So you can take that and use that. So all of these are standard chips which are available in the market, but the same thing can be done, can be designed using Verilog. Obviously, using Verilog, you will be designing a lot more than just combinational circuits. But these are some things that are available in the market. Now this is the interesting slide. So now what happens is, so this is the kind of logic optimization that happens at Verilog and FPGA or ASIC design. This is 3-bit 3-input design. Now this is a truth table given to us, and the requirement is that it should be implemented using a 4 is to 1 multiplexer. But now since there are 3 inputs, how can I do 4 input multiplexer? So I have to optimize my design. So let's look at how to do that. In the first two combination of inputs that we take, when A and B are 0, 0, F1 is the output, is 0, 0. So when A and B are 0, F1 is 0 irrespective of C value. Let's group the other two inputs. When A and B are 0, 1, output F1 follows C. C is 0, F1 is 0. C is 1, F1 is 1. So when A and B are 0, 1, F1 output follows C value. C is another input here. When A and B are 1, 0, F1 again follows C. C0, F1 0, C1, F1 1. So when A and B are 1, 0, output will be C. When A and B are 1, 1, F1 is 1 irrespective of C value. Excuse me. So this is a new truth table that is derived from the original truth table. Now here we had 8 inputs. Here we have 4 input combinations with 2 inputs. Now this can be implemented using a 4 is to 1 multiplexer. So how do we do that? A and B are select lines. I0, I1, I2 and I3 are connected to these values 0, CC and 1. When A and B are 0, 0, I0 value will go to output. What is I0 connected to 0? So F1 will be 0. When A and B are 0, 1, What is the output? What is the output? That value should be C. So it's I1 is connected to C. So C will go to output. AB is 1, 0. C, which is connected to I2, will go to output. And when it is 1, 1, 1, which is I3, will go to output. So instead of using a 8:1 mux, which would have been required here, we are now designing this with 4:1 mux. Because this was optimized, this logic was optimized using this concept. Do you understand this? This what happened here and how we did this?
Yeah.
Any
Yeah.
questions?
So what exactly is the C?
C is just another input. Whatever C value is will go to F1 in case A and B are 0, 1 and 1, 0 respectively.
Okay. Very right.
So the inputs won't change. The inputs to the design we are still three inputs. Three inputs means there are 8 combinations. It's a binary number system. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1 all the way up to 1, 1, 1. Three inputs means I have 8 possible inputs. That will not change. But the output, this logic circuit is instead of 8:1 mux, I'm designing it using a 4:1 mux. So I will get a smaller circuit. Yeah, that's called optimized design. So logic was optimized to design this with a smaller circuit, which will help you in the longer run. So when you consider thousands and thousands of such circuits in your overall design, if you save space, you will save the overall space of your on the chip. So that is what happens on a very regular basis um, after you are done with Verilog. So in the synthesis, after the Verilog verification is done, there's something called logic synthesis, which will do this automatically for you. There is a software called logic synthesis, which will optimize this kind of thing and give you this. So you will do this way, but the logic synthesis output will be this. So this is a optimized output. You're trying to save on the area, so you can using the same chip you can design more and more logic. Okay.
Yeah.
So like a multiplexer, we have demultiplexer, which is reverse of multiplexer. There is one input, there is 2 raised to n outputs and n number of select lines. Depending on the select line, the input will go to one of the outputs. So that is how it's a reverse of multiplexer. So instead of multiple inputs and one output, this is one input and multiple outputs for demultiplexer. Same logic applies. 0, 0, S1 means input will go to output 0, 0, 1, S1, S0. Input will be routed to O1, output 1. This is 1, 0. Input will go to O2. This is 1, 1. Input will go to O3. N number of select lines, 2 raised to n outputs, 1 input. This is a demultiplexer. Can be represented using basic gates like this. Okay. So then we have decoders. Decoders and encoders. Now this is different. If you see here at the block level, decoder is this is how a decoder is shown. There are if there are two inputs, there are four outputs. So n number of inputs, 2 raised to n number of outputs. There is no select line here. How does this work? Let's look at the truth table. When input combination is 0, 0, output 0 is activated, other outputs are deactivated. When input combination is 0, 1, output 1 is activated, other outputs are deactivated. Input combination is 1, 0, O2 will be activated, other outputs are deactivated. Input combination is 1, 1, O3 will be activated, other outputs are deactivated. Decoder means less number of inputs, more number of outputs. N number of inputs, 2 raised to n number of outputs. Okay. Questions?
No.
No.
Okay. So using decoder, now this is a truth table given to you. So let's look at this example that this truth table actually is for a full adder. How do I implement this using decoders? Now, this is a full adder truth table where it has three inputs and there are two outputs, sum and carry out. A, B, and carry in are inputs, sum and carry out are outputs. This is a truth table given to us. Now, if I want to implement this using a decoder circuit, there are three inputs means I have to use 3:8 decoder. So I will use a 3:8 decoder. Let's look at the sum output. When is the sum output 1? When input combination is 0, 0, 1. 0, 0, 1 means O1. Sum output is 1 when input combination is 0, 1, 0. Means O2. Output 2 will be active at that time. Sum output is 1 when input combination is 1, 0, 0. That is O4. Output 4 will be active at that time. And 1, 1, 1 input combination, sum output will be 1. That is O7. Output 7 will be active. So I take O1, O2, O4 and O7. O1, O2, O4 and O7. I OR them, logically OR them. This will give me the sum output. So when one of these outputs is high, this sum output will be high. And when is this one of these outputs high? When input combination will be 0, 0, 1, 0, 1, 0, 1, 0, 0 or 1, 1, 1. Only then one of these outputs will be high, O1, O2, O4 and O7. So that is how sum output is generated using a basic gate in addition to the decoder. Let's look at the Cout condition. When is Cout 1? When input combination is 0, 1, 1, that is O3. Then when input combination is 101, 101 will be O5. 110 will be O6. And again 111 will be O7. So I take O7, O6, O5 and O3. I OR them logically will give me Cout. When input combination is any of these 0, 1, 1, 101, 110 or 111, one of these outputs will be high, so Cout will be high. So using a basic decoder, 3:8 decoder here and two basic gates or gates in this case, I was able to build a circuit, a logical circuit for this full adders. Any questions?
No.
No.
So why decoder? Because decoder, all this combinational circuit takes very small space. So anytime you can design something using combinational circuit, you should try to do that because they take very less space and that will give you very good implementations. So when you do this, when you describe Verilog for this, the synthesis might implement something like this. So you might have learned this using digital logic design. This is logic optimization and logical conversion processes where you design something like this. You might have come across such tasks in digital logic design. So just like a decoder, we have encoders. Now, in case of here, in this case, it's a 4:2 encoder. That means we have four inputs and two outputs. So, depending on which, okay, just a second. Let me put a truth table here also. That will be helpful. So, so this will be okay. So this is how a 4:2 encoder will work. There are four inputs and two outputs. So these are four inputs. I actually should have put it here, but anyways, I0, I1, I2, and I3 are four inputs. And when I0 is high, your output will be 0, 0. When I1 is high, second input, your output will be 0, 1. When I2 is high, your output will be 1 0. And when I3, the fourth input, is high, your output will be 1 1. So you're encoding the input. The output is an encoded format of input. Encoder is more number of inputs, less number of outputs. 2 raised to n inputs, n number of outputs. Decoder is the reverse of that. N number of inputs and 2 raised to n number of outputs. So what we have here is an encoder where the requirement is that, or the way it works is, only one of the inputs can be high at a time. So if I0 is high, output will be 0 0. If I1 is high, output will be 0 1, and so forth. But no, if more, this cannot have a condition where more than one input is high at a time. A normal encoder cannot work on such conditions. A normal encoder will require only one of the inputs to be high at a time. Now, if you take now, but that is not how real life works, right? In real life, there could be a condition where more than one input is high at a time, and you need an encoded output. So how does that work? So in such cases, you have something called priority encoders. Priority encoder will set the priority of an input. So let's again take the example I0, I1, I2, and I3. These are my four inputs, and these are the 2-bit outputs. Now I can set the priority that I0, let's assume that I set the priority I0 is the highest priority, followed by I1, followed by I2, and I3 has the lowest priority. Or it could be the other way around. You can design it the way you want. In such cases, if I0 and I2 is high at the same time, then I0 gets more priority because it is the highest priority and output will be 0 0. If I2 and I3 is high at the same time, both inputs, I2 gets more priority over I3, output will be 1 0. If I1 and I2 is high at the same time, I1 will get higher priority, output will be 0 1. That is how you resolve this priority, resolve this multi input condition at the same time, and then get the output. This is called priority encoders. Any questions here?
No.
No.
Okay. Then we have comparators. So very frequently we'll compare numbers in Verilog, where you need digital circuits for that. So you can compare the two numbers. Typically for comparators, XOR gates is used because XOR gate truth tables support that. We can compare whether two numbers are equal. We can compare if one is greater than other, or one is less than other, greater than equal to other, or less than equal to other. So these are some comparison operations that will be supported in Verilog, for which internally in hardware the comparators will be implemented. Now this particular circuit will implement a equality comparator. So why? Because XOR logic supports that. In XOR gates, if both inputs are different, output is 1. If both inputs are same, output will be 0. So if both, now A and B are two numbers, each of them is 4-bit. A0, A1, A2, A3. B is B0, B1, B2, B3. We're going to do bit by bit comparison. So B3 will be compared with A3, B2 will be compared with A2, B1 with A1, B0 with A0. If both are same, output will be 0 in each case. This is a NOR gate. So if all are 0, in that case the output will be 1. If one of them is 1, the output will be 0. We can say that A is equal to B when all bits of A matches the respective bit of B. So this will give me internally a comparison operation. In Verilog, all I have to do is say if A is equal to B, do something. But internally, this will implement a comparator at the hardware level. Okay?
Yeah.
Yeah. The next combinational circuit that you will come across is our adders. So adders are used obviously for addition purpose. You can add two numbers, but there are different, and there are two outputs normally, sum and carry out. Depending on the adder, there is a third input or there may not be a third input. If you take this is called a half adder. Where carry input is not considered, only A and B value, 2-bit value is considered. There will always be two outputs, sum and carry out. 0 plus 0 will be sum 0 with carry out 0. 0 plus 1 will be sum 1 with carry out 0. 1 plus 0 will be sum 1 with carry out 0. And 1 plus 1 will give you sum 0 with carry out 1. That's how it works. This is a half adder where carry input is not considered as an input. If you take carry input as an input, it will become a full adder. 0 plus 0 plus 0, sum 0 with carry 0. So anytime you have one single 1 in here, sum is 1, carry is 0. When you have two ones, sum will be 0, carry will be 1. When you have three ones, 1 plus 1 plus 1. 1 plus 1 will be 0 sum output with carry 1, plus 1 will be sum 1 with carry output 1. So 1 plus 1 plus 1 will give me sum 1 and carry out 1. This will give me a full adder, which can be represented like this. Any questions?
In the previous diagram, you showed the decoder as an adder, right? So why would you use the decoder as an adder instead of an adder itself?
It was just a task. So
All
nothing,
right.
yeah. So it's not that every time I have to implement a full adder, I'll be instead of using basic gates, I'll end up using the decoder. That was just a way to show you that different combinational logic circuits can be used to design other circuits, other combinational logic circuits. So, but
All right.
yeah, it's not that every time we'll end up doing that. So yeah, any circuit, combinational circuit can be implemented using basic gates, as you can see here. Now this half adder is also implemented using basic gates, and the full adder is also implemented using basic gates. So yeah, so we already saw this. This can be represented in a block format like this. Adders are used basically for addition purpose, as we know. One thing you can see from here is the full adder circuit. Specifically, when you see this carry in as the input, sum and carry out even in half adder purpose. If you see here now, sum is A XOR B, C out is A and B. These are the equations for sum and C out in case of half adder. What about full adder circuit? If you take a full adder circuit, this will be the equation. Sum will be X in, X, Y, and C in our input. So X XOR with Y, XOR with C in. This will give you sum. Carry out will be X, Y plus X, C in plus Y, product of Y and C in. So this will be the carry output equation. So these equations are useful to us later on when we implement specialized adders. So any full adder can be implemented using these equations directly, depending on how many bits you have, how many inputs you have. So the adders now, they are mainly categorized as full half adder and full adder, but the full adder itself can be of different types. What are the different types of full adders that you might end up using? First is a ripple carry adder. Now let's take two inputs. Why is the adder used? We have to add two numbers. Now what are the numbers A and B? A is 16 bits, 15 down to 0 means 16 bits. B is also 16 bits, 15 down to 0. We are going to end up adding the respective bits. So 0th bit of A added to 0th bit of B. For this, if we use single bit adders, now this single bit adder, I will need 16 of them to perform the 16-bit operation, correct? But here I have to use, it's a full adder. So there is a carry in for each adder, there is a carry out for each adder. The 0th bit stage is called adder 0. Now this carry in is the main carry in of the circuit. Carry out of the 0th stage becomes carry in for the next stage, first stage. Carry out of the first stage becomes carry in for the second stage. Carry out of second stage becomes carry in of the third stage, all the way up to 15th stage, where carry out of 14th stage becomes carry in of the 15th stage, and carry out of the 15th stage is the final carry out of the circuit. So carry in of the 0th stage is the main carry in coming into the circuit. Carry out of the 15th stage is the final carry out, main carry out going out. So this is the main carry out. This sum is 15 bits. This is the main carry in. But why is this ripple carry adder? Because this will keep, this is like it goes from one stage to other stage to other stage. So it creates a ripple of carries. That's why it's called a ripple carry adder. Now, the advantage here is it's pretty simple to implement. But there is a disadvantage that to get a final carry out, I have to wait till all the additions have been performed for all the stages. Only then, after the 15th stage addition is complete, only then I will receive my final carry out, for which it will take some time, some delay based on each adder will have some delay involved. So I have to wait till 16 stages of such delays are over and then I will get the final carry out. So advantages is that it is simple to implement. Disadvantage is it's slower because of this delay involved. Okay. Any questions on this adder part, type of adder?
No.
Okay, so how do we overcome this problem? Right, ripple carry adders can be slow. So we have something called carry look ahead adders. So how do we eliminate the delay? We use equations. So what was the delay? What was the problem here generating the final carry out? So we can generate the carry out of each stage, 0 stage, first stage, second stage, all the way up to 15 stage using equations like this. Where are these equations coming from? Here. We saw these equations here to generate the carry. So we will use the equations to generate carry for each stage. Carry 0, carry 1, carry 2, C3, C4, all the way up to C15. In such cases, these carries will be generated parallel with respect to each other. So the delay will be drastically reduced for carry look ahead adder. That's called a carry look ahead adder. So the delay will be drastically reduced. So the problem part of the ripple carry adder was there was a delay in generating the final carry out. The problem is gone with carry look ahead adder. Now that problem is gone, but it has introduced some other problem. To implement all these equations, I need more gates. So it's going to require more area. So typically when you do design, what you end up doing is you have to choose whether you want a smaller circuit or you want a faster circuit. Very rarely you will get both. You can go for a smaller area for your design or you can choose faster speed. In such cases, you will end up using parallel logic and other schemes, other mechanisms to increase the speed. That will end up increasing the area of your circuit. But you have to live with that because that's a choice you have to make as a designer at some point of time. So this is a full adder, ripple carry adder, simpler, smaller but slower. Carry look ahead adder, faster but requiring more area. So depending on which type of design you want, smaller area or faster design, you have to choose one. Or there is a settings and softwares you can set faster design or smaller area. So appropriate adder will be implemented. Okay. Any questions?
No.
Okay. So sequential circuits. Okay, I think I will start this tomorrow. Um, yeah, sorry about that. I just have a bad cold, so I've been fighting the cold very much. So sometimes the focus goes away. So let's talk quickly about the starting time. Is that going to be a problem, or can we at least continue for tomorrow with this time and then? Because by the time I talk to them and again we change something, it will take time, a little bit of time. So for tomorrow, can we continue with the same time?
Oh yeah, okay. Tomorrow should be fine.
Nitin specifically because it's a little problem for you, right? Early mornings.
Yeah, it's very
So
early, so
So at the best, we can push it back by 1 hour. So that's going to be good enough for you.
Yeah, that should be good.
So right now it is 6 a.m. starting time. So tomorrow we'll continue with this 6 a.m. mountain time. So we'll continue tomorrow, but I will talk to those guys to change it to 7 a.m. mountain time starting Monday.
Okay.
All right.
Okay, so and they will send you a email with the change timings. Tomorrow we will continue with the same schedule.
Okay. We should use the same link, right, for the meeting?
No, no, no. They will send you a new link with a new join meeting number. So every time, every class, there will be a different meeting number. So you will get a separate email for it.
Okay.
And as I mentioned, anytime you have a problem, you have questions, you feel free to raise them. If you feel that the training is going too fast or too slow or whatever, you can raise that issue. We will try to adjust accordingly.
Okay.
Okay. So right now it's little faster because I want to go through the basic part of this. Later on, once we start Verilog, if it is faster for you, you let me know. We will slow down a little bit.
Okay.
Okay, sounds good. So we will meet again tomorrow, same time then.